Welcome to the Oxford seminar. This week we have a wonderful guest, Mirco Giacobbe, coming from University of Birmingham to tell us about how machine learning can be used for model checking with neural certificates. So take it away, Mirco.
Thank you very much. All right, so yeah, the talk will be
Sorry,
more...
do you want to turn your camera on so we can see you as well?
Yeah, I can do that. Ooh, okay. All right, so this will be a more applied talk than usual, I suppose. So there won't be any category theory. What I want to show you is a new technology which I and others have been developing in the last few years, which combines in an organic way machine learning and model checking. All right, so, well, we know the motivation of this, right? We're working on the Safeguard AI program. We want to demonstrate, we want to find technologies to ensure that we can trust AI. AI works very well, but we don't have any way to guarantee that AI used in decision-making problems, so we're not talking about image classification or NLP, but decision-making problems. We don't have a mean to have AI technologies that are capable to both have high performance that are proper of modern AI technologies and at the same time being able to satisfy specifications. On the one hand, on the one side, we have the old world, the rule-based AI, which is super safe, but it doesn't work. On the other side, we have the machine learning-based AI, which is amazingly performant, but we don't have proof of safety. So the challenge here is about finding a trade-off, finding an AI that exploits the performance of machine learning and at the same time is capable to follow rules. So again, we're talking about agentic AI. So where we have an agent that takes decisions in an environment and gets information from an environment continuously. So these are control problems, solving games. In general, we're talking about systems that are reactive, that evolve over time. These are normally, for example, solved with reinforcement learning in the machine learning world or with control theory. And the question here that we're asking is, can we enable an AI system, a machine learning system, to prove its own safety, to compute its own proof of safety by using the standard machine learning tools? So this is the question that we want to answer. And if you look a bit, the bigger picture where this falls in is within a framework that combines modeling, learning, checking, and then deployment. So the first step is modeling the world. This is what we are discussing in the theoretical part of the program, where we will define a programming language where we can describe models of the world, so the assumptions that we can make about the world and the specifications of the desired behavior. So this will output a model and a specification of desired behavior. Then we want to obtain machine learning algorithms that are capable to produce policies for decision making, and there are plenty of those that exist already. But at the same time, and here's the catch, they will be able to provide certificate of their own correctness. So it outputs the policy and the proof, which can be checked in composition. Once the proof is checked and its certificate is checked, then we can deploy and we could potentially even compute monitors that check whether anything goes wrong, because we're making assumptions here, which are being propagated up to checking. You want to make sure that when you put it in the right world, your assumptions still hold. So this is what a monitor will do. So this is the big picture. All right, now let's focus a bit on the modeling part as a start. So on the modeling part, our objective is to describe the problem that we're solving. Although we will solve it with machine learning, we want to solve the problem that we're solving as a model checking question. The model checking question is composed of two aspects. A model is what we assume about the world, and the spec, which is what we guarantee, what we want the system to eventually satisfy. Is there a difference between these two? Not really. They can be expressed in the same language if you want. They can be expressed in different languages. It doesn't really matter. What matters is that you can compare them. You need to be able to compare their behavior and to be able to show that what we assume about the world is a special case of the spec, which is what we want the system to eventually satisfy. When we're talking about machine learning, that was the standard model checking question. When we're talking about machine learning, we have another component, which is the policy, which is what we learn. So now, more general, what we want to show is we want to have assumptions about the environment. And we want to show that the environment, when it is composed with the policy, it satisfies the spec. So there are two things here. Well, there are three things here: a model, a policy, and a spec, which are descriptions of systems that have dynamic. And then we have two operators we need to focus on: composition and refinement. We need to show that model and policy, when they're composed, their composed behavior are a special case of the spec. This is all we need from a logical perspective to be able to talk about model checking questions. And clearly this can be augmented with many other components the moment in which you go into assume guarantee reasoning, which is not what I'm going to talk about. All right, so now, verifying systems, verifying machine learning systems is definitely not something that I started. People have been trying to verify machine learning systems for quite a while, but this is the general view of verifying machine learning systems. With having a model of the world and a model and a spec has been there for some time. There have been methods to do that. The catch is that normally the output of learning is the policy together with the model of the spec, which you can still pass. And the model checking question needs to take model, policy, and spec, which are the three components of our model checking question in the context of learning, and verify them using standard symbolic approaches. Now, this can work in principle, but it's very hard. So we're talking about running standard model checking approaches, which can be adapted to reason about, for example, neural networks, if the policy is a network. But still, this is very hard to solve. It's a very hard question to solve a model checking problem. Here's the new view. Here we're talking about still having a similar workflow, but the learning not only outputs a policy and a model and a spec, but also a certificate, which makes checking easier. Not easy, but easier, the model checking. We could even make complexity, we could even make complexity arguments in some contexts. But the point is, what we are doing is that we are taking lots of theories that are within the model checking. We're understanding how model checkers work and transferring most of the burden inside learning. All right. So here we are moving the cards. All right. So there's no trick. We're just moving the cards. I'm just moving problems that this tool still needs to solve and put them in the machine learning component. So they do the same, they solve the same problem, but instead of using symbolic reasoning, this is the world of symbolic reasoning, we solve the very same questions that are inside model checkers, inside the learning. So checking gets easier. So that's what we are doing.
Sorry, does the spec not need to be like a...
Yeah, they need to, yes, they need to. But the thing is that, okay, in principle, yes, the point is that the certificate contains lots of information. So in practice, this is all you need to check, but this is actually a detail. So yeah, logically speaking, you pass everything forward, but I think the point of this slide is this gets easier.
Right, yeah.
The moment in which you add extra information.
Okay, so the spec is sort of inside the certificate.
The spec is kind of the certificate embeds already lots of information about this. Clearly also the model needs to go there. Yeah. A good point to show me the picture. Okay. All right, now solving this question, we don't have yet a very general way to solve this question in full generality. Okay, developing neural certificates as things stand today, but we are making progress into generalizing changes according in the world in which you are. If it's the world of digital systems and if it is the world of physical systems, things change slightly. Although we're getting towards generalizing and having something that can deal with both seamlessly. The digital is the world of agents, the physical is the world of environments. We will have to combine both seamlessly, but as things stand today, we reason about physical systems and digital systems separately. And I will tell you two stories, one in the physical world and one in the digital world. And I will start with the physical. Okay, so let's look at the very first example of model, policy, and spec. So this is a very classical question in the analysis of dynamical systems. We have a model, which is a differential equation, which takes an input. The input is determined by a policy, which is in turn dependent on the state. And we want to show that the policy stabilizes around an equilibrium. So no matter what, every trajectory eventually converges to an equilibrium. This models problems like, well, normally we're talking about error control around the signal. For example, think about your car has an automatic cruise controller. It keeps a constant speed, and it keeps a constant speed regardless of whether you're going uphill or downhill. That's what it's doing. It's doing stability control. The signal, the input signal is the desired speed, and it's controlling the difference. The difference is stable. The difference is zero. So it's trying to, the controller, the policy is keeping the distance to zero. So if you're all of a sudden you're going uphill, it goes down, it pushes it backward. That's what the controller does. Stability control. Okay, so this is the problem. What's the solution to this? To solve this, we need to pull out some cutting edge 19th century technology, which is the Lyapunov function. It's a very classical result in function analysis, in the analysis of differential equations, which tells you that if you have let's forget about the policy for now, but the policy is in there, right? But if you have a differential equation, in the end, if you're in line, this is just a differential equation. To show that the system is stable, you just need to present a function, Lyapunov function, that maps the state into a single real number, and it satisfies these three criteria. First criterion is that the derivative with respect to the system, which is expressed like this, is negative. Anytime you are close to the equilibrium, the function is always positive and it is zero in the equilibrium. So you can think of this as a potential function. The potential, whenever you are decreases with respect to the equilibrium, it doesn't go negative, so you cannot undershoot, and it's zero in the equilibrium. So it means that as the system runs, the potential decreases and you're getting closer and closer to the equilibrium. So it's measuring how far you are from the goal. It's very similar to what we do in algorithms when we develop, for example, an A-star algorithm, which is inspired from the Lyapunov function. It tells you how close you are to a target. So this is very foundational, also in algorithm design. This has inspired computer science a lot. Okay, so this is how it looks, right? So we have, this is our state space. I'm putting Rn on a single line, right? So allow me to do it. And this is the potential. And basically we're saying that as the system runs, the potential decreases. Wherever you are, it's showing, fundamentally you're mapping your high dimensional state space into a one-dimensional system, actually mapping a system into a system. And this one is a one-dimensional system whose value is decreasing towards the equilibrium. All right, so you can think of mapping your system under analysis into a much simpler one, a one-dimensional system that satisfies the property of getting closer and closer to the equilibrium. Presenting this function shows that the system is stable. Okay, now we have reduced the problem into, we started with the differential equations, policies, the spec of stability, and reduced it to the problem of searching for a function. So it becomes as a functional search problem. Now, what is machine learning in a nutshell? Well, machine learning is a functional search problem. Normally, what you have an input domain, pictures, an output domain, classes. So these can be pictures of cats and dogs. You have output domain is two classes, a cat and a dog, classifier. You have a data set, which is examples. So the input domain is actually the type, right? So how large are the pictures? And you have the data set is pictures of cats and dogs. And you have a loss function that tells you how bad you are at classifying. And what happens in machine learning is that normally what you do is you solve an optimization problem. Machine learning is entirely based on optimization. Gradient descent is the technology that enables machine learning. And what machine learning does is searches for a function, for the best function that minimizes the loss. The loss tells you how bad you are, and it minimizes how bad you are at solving the class, at solving and mapping the input into the output over a data set. Yeah?
The sum, the one over the sum, this is the, you're minimizing the expected loss. Is that the idea here?
Yeah,
Okay.
exactly. So this is the expected loss on the data set. So it's the expected loss on
Assuming the data set's
the
uniform.
data that you have. So that's the average. I'm talking about the average here. This is not universal. Now I'm making a big simplification here. Sometimes it's the sum, sometimes it's the average, sometimes it's something else. All right. Now, clearly, machine learning is not searching the space of functions. I'm lying to you. It's not that magical. It's more practical. Normally, what happens is that you fix a function, you fix a parameterized model, and you search in the space of parameters. So it's a first-order problem. So it's just an algorithm that runs gradient descent and searches for numbers. That's much more practical, and that's why it's so successful. So what you do, normally you fix a parameterized model. So you tell me what is the space of functions, for example, a polynomial, and you ask, give me the right coefficients. So find the coefficients that minimize the loss. Now, this is much more restrictive than what I told you before. How is machine learning working so well? Well, deep learning has found the best balance between searching for functions and searching for parameters. What they're saying is that their parameterized model is a neural network, which, if large enough, is a universal approximator. So let's just say that it's a powerful approximator for now, because I'm not exploiting universal approximation theorem. It's a very powerful approximator. The larger it is, the more it expresses. You don't really need to look into how the neural network is. You just put more neurons, you get more expressivity. Normally, that's really how it is. Unless you want to do some very sophisticated thinking, but most of the time it's just more neurons, more power. And you're searching for the parameters of a neural network. And this is kind of a proxy to search in the space of functions. Okay? So now we started that the stability problem was searching for a Lyapunov function. We're saying that deep learning is searching in the space of functions. You see where I'm going, right? Searching for a Lyapunov function using machine learning can be expressed as the problem of expressing the search of the Lyapunov function as an optimization problem, as I showed you before. So the idea is that we want to design our Lyapunov function, whose input domain is the state space of the system. Output domain is the single number, single value. And we want to design a data set in a loss function such that once the loss is minimized, this will be a Lyapunov function. So now we know the type. It's mapping the state space of the system into the state space of that single value process I told you before. And here the game is, how do we design a data set and a loss such that once minimized, there will be a Lyapunov function. All right, so let's remember our criteria. The derivative with respect to the system is negative, the function is positive, and is zero in the equilibrium. I should change this. It's not relu, but it's quadratic activation in this case. Right? So now, one of the first things that you need to do when designing a neural certificate is trying to get rid of as many criteria as you can. Okay, this is a practical matter. The more criteria you have, the harder it is to optimize. We're talking about using numerical algorithms in the end. So you really need to, so one thing is you need to try to make life easy to the optimizer. One of the things that you can do is when you have multiple criteria, get rid of as many criteria as you can. And these two are easy to get rid of. So having a function that by construction, a parameterized function that by construction is 0 in a point is easy to do. You just shift it around that point. So you basically can make this the equilibrium. So this is saying, let's have a neural network without biases. But there are many ways to do it. One way is to have a neural network without biases. Make sure that it's non-negative everywhere except in that point. Use quadratic activation functions in the last layer. In the layers before, you can do whatever you want. And now all you're left to do is to minimize the gradient with respect to the system. This stuff is all differentiable, right? This is no more than using what already exists in the framework. It's using autograd. So this is straightforward to encode as a problem. And so what we're doing is we are minimizing exactly this. We're minimizing exactly the gradient of V with respect to the system. Now the policy should appear there. Right now it's not appearing on the slide, but it should appear there. So what we are doing as you're minimizing the parameters of V and the parameters of the policy such that this value becomes negative. So if this value is positive, this gives you a value. So it's trying to minimize it. We'll try to minimize it. As soon as it goes slightly negative, that's why we have a delta. Then you're happy. Then this gives 0. If this value is negative, this gives 0. When the loss is 0 across the data set, when the data set will be a sampling of the states, then you're happy. At least you know that your function satisfies the Lyapunov criteria on your sampling of the data set of the state space.
Sorry, can I ask about quadratic activation? So the point is you can, if you've got a function that satisfies 1, you just manufacture one that satisfies 2 and 3 as well.
Yeah, manufacturing 1 is harder, right, by construction.
Yeah.
So what can we do simply by construction? These are these two.
Mm-hmm.
So if you put a quadratic activation, let's say that let's replace xc with equilibrium. Mm-hmm. So it's a perfectly quadratic function. So x squared, that would be 0 and 0 and positive everywhere. Mm-hmm. So you can get rid of these two criteria. You know that they will always be satisfied. Now you need to find the other parameters of your neural network such that this holds. So imagine
the last layer, you do something quadratic that forces everything to be positive.
Yeah.
And then you also shift by whatever you need.
And then you shift by whatever you need to put the equilibrium in the right place, and then you optimize. You optimize for that. If you could do that by construction, then we will be good to go. But doing that by construction is hard. The hard thing is, what is hard is being able to satisfy all the three at the same time. So what I'm saying is that if we can get rid of as many as we can, let's do it. This is actually the trick that makes it work in practice. Okay, so once you're done, if you minimize this loss, you have that on V, which is your final sampling of the region of interest. Your function looks like a Lyapunov function. Is this a proof? Not yet. What you need to do, once you have a candidate certificate, you have your criteria, you turn it into a loss function as I showed you, you give it to the learning. What you have to do is to check whether on the entire state space, the function, the derivative of the function is actually negative. So this becomes a satisfiability checking because you're asking the question, does there exist a state for which this is not true? If you have a counterexample, you may want to feed it back and train again. But the point is, now, once we have a candidate certificate, what we need to do here is to check using a satisfiability solver, for example, or neural network verifier, whether there is a counterexample to the claim. This is still a hard question, but it's much easier than model checking the whole system. Finding a Lyapunov function is an undecidable problem in general. We are checking whether a given certificate satisfies this criterion is something for which there are decision procedures. But turn an undecidable problem into a decidable one. What's the trick? Well, the trick is that learning is incomplete. Okay, it works in practice, but it may not work all the time. But the thing is that we're anyway looking for policies in unconstrained environments here. We're classifying cats and dogs. So this is not completeness we're after. What we want is soundness. And this is sound.
Sorry, so just check. So in the learning phase, you optimize to find a potential Lyapunov function, and then the checking actually tests whether he produces.
The checking test.
Actually verifying that something in
Yeah.
Lyapunov can be done algorithmically quite well.
Exactly. And now here, now that there is also, this is not what I will talk about in this talk, but there is lots of playing that you can do here, because here you may want to say, I want to give hard guarantees. Therefore, I will use a RSNT solver. But in many contexts, you may not even want to give hard guarantees, because in practice, it doesn't matter. If the model is an approximation of the world, giving hard guarantees on an approximation is probably not a good idea. So you can actually think of speeding this up and give statistical guarantees with certain intervals of confidence. There is lots of playing that can be done here to scale it up. Now, what I will talk about is this, because it's the most funky part. But there is lots of research also to be done here. Okay, so when you have a loop that gives counterexample, this is how it looks like. So you first optimize on samples, you'll get a candidate. This is the level set, this is the zero level set, and this is the region of interest. As you can see, there are some parts that are positive, that are above. So what you have a counterexample. You take a counterexample, maybe you want to use it to sample around. Having more sample doesn't hurt, right? So, and then what happens is that you retrain, and this will be pushed back. Up until it's being pushed out of the region, and this is negative. The V dot is negative everywhere. So this is the effect that you have if you exploit the counterexamples. All right, now back to the point of deterministic guarantees. Here we're assuming that we have a perfect model of the world, and we're actually trying to achieve guarantees. Is it reasonable in AI settings? Many would argue that this is not reasonable. Therefore, we would like to reason probabilistically. So now let's generalize this concept. Let's talk about the stochastic system, where our model is the stochastic differential equation, which is fundamentally a differential equation with a drift. Right? So with this is up until here, it's a standard ODE, as it was before. But now this becomes a random variable. The derivative on time becomes a random variable because it depends on another random variable here, which is added to my original ODE through something that is called a diffusion. So stochastic differential equations are expressed in terms of an ODE plus a diffusion term. So this will fundamentally, this outputs a matrix which modifies this random variable and makes it compatible with the process. Okay, this is called an Ito process. It looks very specific, but it turns out it's very general. It expresses lots of models. Okay, the policy will still be a neural network, and let's also make it a bit more spicy. Instead of stability, let's talk about something that is a bit more high level, and we go more higher level in the talk. Let's talk about reach avoidance. So we have a subset of the system, which is our target set. We want to reach A while avoiding B. Okay, so we need to generalize the Lyapunov functions in two directions. First, we want to have a more general system and a more general spec. Okay, how does it look? Well, we start from an initial state, and we have our set that we want to avoid, our set we want to reach, and we want to show that no matter what, the policy will always, no matter what happens with randomness, the policy will always take you to the target and will not hit the bad set, the set that you want to avoid, with a certain probability. Also, we need to be able to quantify the probability. We may want to prove this almost surely if it's possible, but if not possible, we may want to show what is the maximum probability for which this happens. And the trick is the following in this case. So here, it's a Lyapunov function for stochastic systems, which combines Lyapunov theory and martingale theory. And what we need to compute is what is known as a super martingale certificate. So it's a variation of what we had before. So it's a function that is upper bounded by some constant in the initial condition, is lower bounded by some other constant in the bad state, and the derivative, the stochastic derivative. This is called the infinitesimal generator. I'm not showing you the equation, but think of it as the stochastic dual of the derivative. It contains the Hessian of the drift operator, is negative. So this value should be negative. Okay, so these are negative coefficients. It's much smarter. I do this.
Okay.
Right, so they're all positive. Three positive coefficients where beta is larger than alpha, and it satisfies these three conditions. So it's the same game. We have some conditions that we need to satisfy. I'm not going to show you the loss, because I'm sure that has seen the example before, you can figure out how to design the right loss here. But we know that if we satisfy these three properties, the probability of reach avoidance is lower bounded by this. So alpha and beta is the probability of not satisfying this. It's an upper bound of the probability of not satisfying it. Therefore, 1 minus alpha over beta is a lower bound of the probability of satisfying it. Okay. Okay, let me give you an intuition of what happens. So what happens, this will look like this. So it's still a Lyapunov function. Now, the picture is very similar as it was before, but there is a bit more elements. Now, this is the A, the set that we want to reach, and this is B, the set that we want to avoid. And these are level sets. So we're playing with the level sets now. That's how we describe probability. We're playing with the level sets of the function, and we want that as the function goes in the avoidance, the value is larger than beta, and in my initial condition is less than alpha. And the stochastic gradient decreases. So the probability gets closer and closer to reach. So you can think of it as the function. This would be a super martingale. So so it's an upper bound to the martingale process, which describes the probability of escaping. So replace beta with 1 for a moment. You can think of this as the probability of escaping. When you're here, it's 1, so larger than 1, but it's 1. And as you get closer to your target, it gets smaller and smaller. So this is intuition, but it is a Lyapunov function in the stochastic world, and this is connected, it turns out, to the martingale process that describes the probability of satisfying the spec. The two concepts are unrelated to each other. Here we are making a relation. We are relating the Lyapunov function. Well, we're not the first to do it. Okay, this is actually a well-known concept since the 60s. But fundamentally, the idea is that the martingale process that describes the probability of satisfying a specification and Lyapunov functions are related to each other. So if you play with the level sets, you obtain the probability of them satisfying the spec. So the violation probability gets smaller and smaller. This is what it's telling you. While before it was potential, now it's probability. On higher dimensions, this is how we look. Imagine these are two bad states that you want to avoid. This is your initial condition, and this is your target. Computing a super martingale fundamentally gives you the landscape of probability. So imagine you're in your high-dimensional space, you're actually seeing the landscape of risk. The higher the value, the higher the probability of not satisfying the spec. This is what happens. This is how it looks. Here is very low, and here is very high. So now imagine, as you train a certificate, you should imagine that the AI system is having the landscape of risk. Okay, so it sees high values where danger is, and low values where the system is safe. And it has to navigate at the bottom of the valley. That's what happens. And this is what it's doing here. The system is navigating at the bottom of the valley. So this is providing a landscape of risk.
What happens if like the setup of A and B is like fundamentally unsolvable? Like B is some subset, it's like a ring shape, and A is inside of it, and your initial point is outside. So there's no way to get to A without passing through B.
If there is no way, this will be high everywhere. And there's just no valley. Right, so you will get a trivial upper bound. In this case, you will get a trivial lower bound, and the lower bound will be 0.
Okay.
So basically, you can't say anything. Now we need to talk about upper bounding. So this is what we're working on. But if it's unsolvable, you get a trivial result, and so you get a super martingale that is useless. So again, no completeness here. We give the criterion that you need to satisfy, but we're not guaranteed that you will always satisfy it. Okay, now we switch from deterministic systems and stability properties. We went to stochastic systems, which avoid property. Do we really need to write a paper for every case? We would like to generalize, right? We want to go towards the paper that proves them all. So that where you can describe a very general system, a very general spec, it tells you how to compile it down into the right loss function, and then we're done. To work on something else. We haven't got there yet, but I tell you an ingredient to do that. Okay, so now we really generalize the systems quite a lot, but the specs, there is more. So one further directions we can take is to think about specifications expressed in linear temporal logic and even beyond potentially. But here's a start. So imagine that we could have a logic, there's a grammar that generates it, where we have atomic propositions. Atomic proposition would be expressions that tell you, that describe the set, okay, the bad set, the target set. It will be predicates of the state space. And that can be combined with propositional logic. You may have predicates where you can make conjunctions, disjunctions, negations. And on top of that, you can describe how they are satisfied over time. So you may say that something is true immediately after one step. Something is always true throughout the entire execution of the system. Something will eventually be true in the future. Or that something is true until something else is true. So now we have a programming language for specifications. We will have to take a general programming language for specifications and translate it into the right loss function. Let me make you a few examples of linear temporal logic. For example, you want to say that we eventually in the future satisfy that the value of x is greater than 100. This will be fx greater than 100. Finally, x greater than. We want to avoid harm until we reach the target. So we reach the target, and before that, we're not observing harm. Okay, so not harm until target. We reach and then stay within the operational parameters. It means that there is a point in the future such that from that point on, hope is always true. And hope is some predicate that I have. Or we can say that we repeat a task infinitely many times. This can be useful, for example, if we want to talk about availability of a system. We want to have a system that is like robust to adversarial denial of service attacks. So you want to be able to always repeat a task. You never starve. Right? So this is globally finite task. This means that it's always true throughout my execution that in the future, I will be able to fulfill the task. So at every point in time, there is a point in the future such that I can fulfill the task. This means I can fulfill the task for infinitely many times. It doesn't mean that I fulfill it continuously. It means there is always a point in the future that fulfills it. Every request is eventually being served, right? So availability. It means that it's always true that if I see a request, it implies that from that point on, in the future, with respect to the request, I will be able to serve it. Right, so now we have a programming language for specifications. This is going back to the model checking question. This is the LTL model checking question, which has been studied a lot in the context of hardware design. So we talk about hardware designs. Let's forget for a moment about differential equations, but here is also where we get compositionality very nicely. We can learn a lot from hardware design. Okay, now the model, for example, is a system Verilog design, which has modules, which has shared variables, which has a notion of composition. And we want to show that it satisfies what is known as a system Verilog assertion. This is actual code, is an actual standard that is used in circuit design. So model checking is industrially applied in a hardware design. It's the only place where it's industrially applied. In every other domain is academic. Here it's industrial. Okay, so now this is a system that describes the dynamics of a circuit. So the circuit has registers, and it tells you how these registers are updated. So it's a dynamical system if you want. And the specification is fundamentally LTL. For example, this is saying here we have here we have a counter that tells you how that describes a buffer, how many elements have in a buffer. It can be full, it can be empty, right? The counter of the elements. And then say that eventually will be full, eventually will be empty. So it will be full infinitely many times and empty infinitely many times. That's what it's describing. So it's LTL, so it allows me to describe very complex properties. And now, how do we get from this into our nice objective loss function? We need to do a bit more work here. So first, we need to describe what is the semantic of refinement. So now, without going, well, here you need to imagine a bit what happens. So we need to be able to describe both in terms of languages. So this needs to go up in the direction of languages and automata. So imagine that the system describes a language of infinite traces, where every word are the values of my variables, the sequences of variables of my variables. Okay, this generates sequences of variables valuations. And a set of sequences, what is it? It's a language. That's what we know as a language in automata theory, where every element is a word. A specification is also a language. This is the language of all the traces that satisfy this property. So this is not something that we will construct, but ideally you can think of this as the set of every word where I see full and I see empty infinitely many times along each word. Right? So what they have in common is the signature. They need to talk about the same variables. Now, the moment in which you describe both in terms of languages, model checking, so answering the refinement question, the model checking question is language inclusion. We need to show that every word in the language of the model is a word in the language of the spec. Okay, so it's language inclusion, which can be solved in many ways, but the standard canonical way from the textbook is by turning it into a language emptiness question. So what we do, we consider the dual. So we consider the language of the negated property. And if this intersection is empty, then inclusion holds. Basic set theory, no magic. No magic here. Okay? This is the complement of the previous one. Okay? So now we need to make the intersection of two lines. Negating a formula is easy. Just stick a knot in front of it. And now we need to be able to do intersection of languages and checking for emptiness. How do we do intersection of languages in practice? Because we're not going to construct this. Neither this. I mean, these are infinite objects. We're not going to construct any of this. So we need to be practical here. The catch is that every LTL formula admits a visual automaton that accepts exactly the same language. So you can take your negated formula, which I have negated it for you. So seeing full and empty infinitely many times is equivalent to see either of them finitely many times. This is what this is saying. And this corresponds to a visual automaton that accepts the same language. A visual automaton accepts if you see the accepting state infinitely many times. So what is it saying? This is saying that I'm staying in Q0 and non-deterministically at some point I decide that either full or empty will not be shown anymore. This means I'm violating the property. So at some point I decided I'm not going to see full anymore, and I keep not seeing it. So these are non-deterministic visual automata. There is an oracle that tells me at some point you can stop, and you don't see full anymore, or you don't see empty anymore, and you stay there. If you saw full here, you won't have a transition, right? So this means these blocks. If these blocks, if any of these two modes is blocking, it means there is an event that forces you to exit. So if it's terminating, it means that the automaton doesn't accept. If the automaton does not accept, the property is satisfied because this is negation. Okay, so what I need to do is to show that this automaton never accepts. Which means I need to show that the accepting modes are visited at most finitely many times. Because the accepting condition is visited infinitely many times. So it's a termination question. I need to answer a termination question on the product between the system and the automaton. I take my system, I take the automaton, and I need to show a termination question. This is what I showed before, right? Emptiness is inclusion. So I compose the two systems, and I solve the termination question on the composed system. Once I compose them, the accepting conditions of the automaton become the accepting condition of the entire composition. And there, I still need to look for something that resembles a Lyapunov function. That would be a ranking function. It's a Lyapunov function that takes the state of the system S and the automaton Q, and it's non-increasing everywhere, and it decreases every time you see an accepting condition. This function will be bounded from below. Okay, because the state space is finite. So if I decrease every time strictly, and this maps into the natural numbers. If I decrease strictly every time I see an accepting condition, this is what I will have. I will have that this is the indicator of the accepting condition. F is accepting. Every time I see an accepting condition, the value decreases. This means, as this is bounded, this means I can decrease at most finitely many times. The automaton doesn't accept. If the automaton never accepts, the property is satisfied. So turn the general LTL model checking question to that of finding a Lyapunov function again. So we've done this with the V being our Lyapunov function. Forget about this. This is like a detail. But V is our Lyapunov function that behaves like that. And we compare this with industrial tools that do LTL model checking. And here's how it looks. All right. So we took a bunch of tasks taken from a textbook and scaled up to make them harder and harder. And we compare with two standard model checkers, ABC and XMV. These are two standard academic model checkers. And you can see that within 5 hours time limit, ABC solves 25% of the tasks. This gets to 60% of the tasks, but it scales not great, right? This is log scale. If I compare it with an industrial model checker, we're talking about something that costs money. For some reason, after 15 minutes, it finds the strategy. I have no idea what it does. It's closed source. But as tasks get harder, it also starts struggling. By using neural certificate approach, we have a completely different trend. Okay, now to help you read this plot, where the industrial tool takes 5 hours, we take less than 40 minutes. Where that takes 5 hours, so it takes 8 minutes. Where ABC takes 5 hours, R2 takes 3 minutes. Also no extreme, with extreme minutes. But it's like to show you the different scalability trend. It's like, because it's a long plot, so it may not be easy to see what's happening. Okay. Now, all right, so this is the trick. So you turn the LTL model checking question into finding a Lyapunov function. We did the same with stochastic systems. It's all about Lyapunov functions. All right, now can we combine it? Can we talk about stochastic systems and temporal logic at the same time? Can we find the ultimate neural certificate? So imagine that we could describe our system with a differential equation or something hybrid that combines differential equations and digital system, a generalized stochastic hybrid system. And where we could put a general LTL model checking formula. Then this would translate into an automaton that tells you what are the Lyapunov criteria. So we have an automaton that according to what is observed, it changes mode. And according to the mode in which it is, it tells you that if you want to satisfy the spec, the function needs to decrease on this state. It needs to increase in some other states. The negation will also have some criteria. If we had that, we would be able to describe, this is the probability of satisfaction of the spec. Imagine this is black to be the probability of satisfying the spec. If we will be able to compute a lower bound, as I showed before, right? I could compute lower bound of the probability. We'll be able to compute lower bounds on the satisfiability of the spec and lower bounds on the satisfiability of the negated spec. So we'll be able to compute upper and lower bounds on the probability of satisfying an LTL spec on a stochastic system. We haven't done this, but this is where we're going. Okay, so yeah, this concludes the talk. This was an overview of neural certificates, which myself and many others have been playing with. There are results on the continuous time deterministic system, the Lyapunov neural networks. This is the first thing I talked about. They are dual on the discrete size systems, which have been applied to software and hardware as determination analysis in discrete time dynamical systems. Their probabilistic extension, which combines Lyapunov function with martingale theory, the neural supermartingness applied in probabilistic programming and in MDPs. And the one I mentioned with stochastic differential equation, which goes into the continuous time, and our goal is to really fill this picture. And this is it. Thank you very much.
Thank you, Mirco. That's wonderful. Do we have any questions? So you said you wouldn't talk about assumed guarantee reasoning, but I wonder, what do you think is like the most crucial thing that you would want to see for assumed guarantee reasoning, and why is it difficult? That's really
no, it's not difficult. It's just it's the next thing to do.
Yeah.
Right. So assumed guarantee reasoning is always there, right? As I mentioned at the very beginning, there are these two operations. We need to be, so the two ingredients to talk about model checking are composition and refinement. Here we're talking about monolithic systems. So we're treating everything as monolithic. Assumed guarantee will allow us to break the problem into many pieces. The ingredients are there. Here we are focusing a lot on expressivity and less on compositionality. Talking about compositionality is the next step. So we haven't done it because it wasn't in our priority so far.
Cool, thanks.
So that's like taking these, you're building Lyapunov functions for component systems and then synthesizing them to.
Exactly, and then you want that this Lyapunov function tell you something about the general system. Yes. So I think that's something that needs to be done now. It's the next step. And there are notions of compositionality of Lyapunov functions that come from control theory already. So compositionality is not something that we need to invent. It exists. The thing is that it has never been framed in the context of assumed guarantee reason, which is more proper of digital designs. Again, we need to do the same exercise I've done here, where we are starting to get inspired from Lyapunov functions and combine this with automata theory and model checking and see whether there's a common ground. And there is a common ground. It's all about writing a paper that shows, hey, both theories are special cases or something more general.
Sorry, and I have a very basic question. So I didn't get, so what is the role of the neural network here? So the machine learning, so the role of the machine learning here is, are we building a machine learning model and then check the safety of the machine learning model, or we use machine learning algorithms as part of the safety check?
Both. So we are using the machine learning to make the safety check easier. So we're using the machine learning to make the safety check easier. So what happens is that the safety check in general will be very hard. So now the question is, can we extract some of the questions the model checker needs to answer if he wants to verify a system? And one of the things that the model checker needs to answer is to find Lyapunov functions. Also invariants. Loop invariants in software verification are special cases of Lyapunov functions. Okay, so when you want to prove that the system is safe, you have plenty of proof obligations that are all trivial apart from specific spots, and these are the construction of a Lyapunov function. So what I'm saying here, how about we keep all this sketch of proof obligation? We kind of understand. We keep what we know from the verification of systems. So as to, and then we transfer the hard bit into the machine learning component, right? So it goes in both ways.
Okay.
Okay, so we are still verifying the system, but we are transferring parts of the obligations that we will need computer safety proof into the machine learning component. All right,
Yeah.
so we are using machine learning to help safety, to help a verifier, which helps the machine learning component. So I see why you got confused, because this is like it's circular. It's circular by design. That's really what it is.
Yeah, thank you.
I have a question sort of just about Lyapunov functions. So you described building Lyapunov functions for continual systems and for discrete systems, and it seems they're sort of doing different sorts of things. Is it sort of easy to combine these to get like Lyapunov functions for hybrid
Just
systems?
doing really different things. They're more similar than you think. So in one case, I wanted the derivative to be negative. In one case, I wanted the difference between current and next state to be negative. The difference is the discrete time derivative.
Right.
So it's very similar. It's a very similar concept. So instead of having the nabla, and the other way around, and you have the delta. But it's very similar.
And can you combine these quite easily for hybrid systems, or
I don't know yet.
okay.
I think it's one of those things that are easy once you solve them. All right.
Are there any further questions? If not, let's think Mirco again.